Hi everybody. In this video we're going to be talking about something called a volume of revolution. And the idea is that we take a two-dimensional area and we revolve it around an axis to create a solid shape. I encourage you to go online, look up lots of pictures of this. In this video I'm just sort of going through some of the basic technical ideas of how you do one of these problems. Okay. I'm starting with a diagram though that is two-dimensional because that's what I want to encourage you to do. I want to encourage you to get all your information sort of in order before you start trying to figure out how to find a volume or even what method you should use. So here, my two-dimensional region, my area that I'm going to revolve around some axis, is bounded above by the function f of x equals 1 minus x squared. It's bounded on the left by x equals 0 and bounded below by y equals 0. So I get this sort of region that's flat on two sides and curved on the third side that I can revolve around different axes. Okay, before I do any of that, before I even consider any sort of volume, I'm actually drawing a diagram very similar to the diagrams that I drew when I found areas. So I'm trying to build on ideas that we've used previously. Okay. So I imagine that this area is made up of lots and lots of little rectangles. Each rectangle has a width delta x and a height f of x. The center of the rectangle is a distance of x away from 0. And here I also added that it's a distance of 1 minus x from this intersection point, which is the root of f of x. So f of x intersects the x-axis at 1 and back over here at -1. And so I included that distance. Okay, so this is a lot of really sort of basic information about this area that I've made note of before I talk about any sort of volumes. Okay. Now we're going to look at three different ways we can get a volume from this region, but what we're really going to focus on is what's happening to this rectangle. Because what is happening to this rectangle is going to determine how we solve the problem. All right. In this first example, I'm using something called the disk method. So I want to imagine that I'm revolving this trapped region around y equals 0. So that's the x-axis. But again, I'm focusing on this rectangle. And when I look at the rectangle, I see that the rectangle, this flat edge of the rectangle, is always touching the axis. So no matter where I drew that rectangle, from 0 to 1, the rectangle is always touching the x-axis. What that means is that when we revolve around that axis, I'm going to get a solid disk, a solid puck. Okay? There's no hole in the middle at all. The width of the puck is always the width of the rectangle. That's my delta x. And the radius of that puck, the radius of that disk, is equal to the height of the rectangle, and that's f of x. So the volume is going to be pi r squared, that's the area of the circle, multiplied by the width w. When we turn that into a rectangle, or turn that into an integral with our different values, pi is a constant, f of x is our radius, and so I have f of x squared, and then the width is going to be dx, because as we take a limit, as the rectangles get thinner and thinner, delta x becomes our differential dx. Right. And so what we're left with is this disk shape, and the integrand, the pi f squared dx, is the volume of a single disk, and the integral represents the process of adding up these infinitely many, infinitesimally thin disks. So sort of, like I said, I encourage you to go online, look at lots of pictures of volumes of revolution. They can be interesting, but I really want to emphasize this idea that I knew this was the disk method because of what was happening to this individual rectangle that's the same sort of rectangle we talked about when we looked at Riemann sums and when we looked at areas between curves. In this next example, I'm going to be using something called the washer method. We're going to get a slightly different shape here if we revolve our region around the line y equals 1. Okay, but again, I'm going to focus on that rectangle. I'm going to focus on the rectangle that we looked at for Riemann sums and areas. And what I can see is that unlike the disk method, the rectangle isn't always going to be touching the axis. Back here, if I drew a rectangle at 0, the rectangle would touch the axis. But if I draw a rectangle any place else, that's not happening. All right, the rectangle stops short. So what that means is that when I revolve around the axis, I'm going to end up getting a hole in the middle. So to find the volume, I'm going to find the volume of the entire disk and subtract out the volume of the hole in the middle. That means that I get the equation pi times the quantity capital R squared minus little r squared. So that's the radius of the whole disk minus the radius of the hole in the disk, multiplied by the width. All right, so what are our radii? Well, here's our axis, and to find the larger radius, I go to the far side of the rectangle. So I start at the axis, and I keep going until I get to the far side of the rectangle. So the far side of the rectangle is always on, in this case, the far side of the rectangle is always on y equals 0. So the distance from y equals 1 to y equals 0 is 1, and so that's where I get the 1 squared. The inside radius, the little radius, is the distance from the axis of revolution, this axis we're revolving around, to the near side of the rectangle. So I'll go from 1 to this near side, but that near side is at a height f of x. This is why it was helpful to draw that little rectangle and label it before I started trying to solve the problem. So the inside radius is going to be 1 minus f of x, and so that's where I get the 1 minus f of x squared. Pi is a constant. Dx is what delta x becomes when we are adding up our infinitesimally thin rectangles. And I'm integrating from 0 to 1 because I'm starting at 0 and I go to this point here, which is x equals 1. So I would evaluate this integral in order to find the volume if I revolved around y equals 1. Okay, here's one where it kind of looks like a washer, but it's not. This is called a cylindrical shell. Like a washer, I have a circular shape with a hole in the middle. But unlike the washer, the thickness or height of the circle changes. The thickness or height of the circle is going to be the height of the rectangle, which is f of x. And the width of the rectangle, the thickness of the wall of the shell, this is called a cylindrical shell, is always going to be delta x, which means as we take our limit, as we let our rectangles get thinner and thinner, the thickness of that wall is going to become infinitesimally thin. All right. So it has a hole in the middle, but the height is variable and the thickness of the wall becomes infinitely thin. So this is a cylindrical shell problem or a shell method problem and not a washer problem. The other way I know that this is a shell method problem and not a washer problem is because all my rectangles are parallel to the axis of revolution. So if I look at the height of my rectangle, my up and down height of my rectangle, it's parallel to my axis of revolution. So that's another way that I can identify that this is a shell method problem and not a washer problem. Okay, so to find the volume of that shell, it's 2 pi r, which is the circumference of the circle, multiplied by the height of the circle, multiplied by the width of the shell. Okay, so if we were doing this in a Riemann sum, in a finite case, the formula would be slightly different. But as we take the limit, this is the formula we end up with. Okay, so what we have here is 2 pi times 1 minus x, which is our radius in this case, because it's the distance from x equals 1 to the center of that rectangle, times f of x, which is the height of the rectangle, times dx, which is the infinitesimally thin width of the of the shell, of the wall of the shell. And so this integrand gives me the volume of a single shell, and then the integral is adding up that volume from x equals 0 to x equals 1. Okay, so that's the third method for volumes of revolution. The problems could vary a lot, and they're difficult in terms of visual in difficulty, depending on how hard they are to visualize. But those are the basic ideas and the things you want to look for. And I really want to emphasize this idea that you want to start with the two-dimensional figure and think about how you would divide it up into rectangles if you were doing an area in a Riemann sum, and then focus on what happens to that rectangle when you revolve, all right, because that's what determines your method of solution. All right, that video was a little longer. In our next video, we're going to talk about arc length, and I'll see you later for that.